At 6:14 on the morning of November 3, 1943, the destroyer USS Brownson was not at the Philadelphia Naval Shipyard. She was operating in the Southwest Pacific. But at that same hour, Dry Dock Number 3 on League Island was receiving a heavy cruiser that had taken a torpedo hit southeast of Bougainville 6 weeks earlier. The tugs had her positioned by 0630. By 0700, the dockmaster had begun flooding down. What happened next was not dramatic, at least not from the outside. Valves opened. Water entered the dock. The ship's hull settled into the keel blocks at the dock floor. The water dropped. A cruiser that had steamed into the Delaware under her own power was now resting in a concrete chamber, with her keel 40 feet below the waterline of the river outside the caisson gate, and 40,000 workers about to begin taking her apart. And the Philadelphia Naval Shipyard at League Island occupied 904 acres at the confluence of the Delaware and Schuylkill rivers in South Philadelphia. Of those 900 acres, 360 were covered by working industrial plant. 390 buildings totaling more than 7 million square feet of enclosed shop floor. 5 graving dry docks. 29,000 lineal feet of berthing. A 350-ton hammerhead crane, the largest in the world when it was installed after the First World War, that could lift a destroyer's entire machinery plant clear of the keel. At the wartime peak of 1944, the yard employed 47,596 full-time civilian workers. That figure does not count military personnel, contractors, or the high school students the Navy brought in during summer months, when total occupancy on League Island exceeded 60,000 people on a single working day. 53 ships were constructed here during the Second World War. 1,218 were repaired, converted, overhauled, or dry docked. But the number that tells the story is not the ships built. It is the ships returned. League Island was not simply a place where ships were repaired. It was a self-contained heavy industry complex built to a specific and demanding set of specifications. And those specifications had been set by the warship itself. A damaged or worn-out naval vessel arriving at the Philadelphia Naval Shipyard was entering an industrial system organized to address every category of failure a warship could sustain. The 5 graving dry docks were the entry point for work below the waterline. Hull plating, propeller shafts, rudders, sonar domes, sea chests, and the keel structure itself. But the dry docks were only the staging platform. The work that happened after dewatering required the entire surrounding complex. The machine shops handled precision work, propeller shaft alignment, turbine blade inspection and replacement, and gear reduction unit overhaul. The pipe shop dealt with the miles of copper and steel tubing that ran through a warship's engineering spaces. Steam lines, cooling water circuits, fuel systems, fire mains. The electrical shop worked the wiring, the switchboards, the combat system power distribution. The boiler division addressed the engineering plant's primary heat source, the oil-fired Babcock and Wilcox, or Foster-Wheeler boilers that produced the high-pressure steam that drove the turbines. When a boiler burned through a tube bank or suffered a corroded superheater section, that work came to League Island. The foundry propeller shop, built around 1919 on the western end of the island, was the yard's casting and propulsion component operation. By the end of the Second World War, it had produced more than 5,500 bronze propellers for United States Navy vessels, every one of them cast, machined, and balanced here on the bank of the Schuylkill. Before we go further, if this kind of story matters to you, consider subscribing to the channel. Every video here is built around the systems that actually moved America. The rail yards, the port operations, the industrial facilities. The infrastructure that most people never thought about until it stopped working. Every naval battle the United States won in the Pacific depended on warships that had been repaired and returned to sea by workers on League Island in Philadelphia. Men and women whose names appear on no monument. Did you or someone in your family work at the Philadelphia Naval Shipyard? What shop were they in? Pipe fitting, machinery, or electrical? The boiler division. And what class of vessel were they on when the war ended? The high-pressure steam turbine overhaul methods Philadelphia developed for Iowa-class battleships in 1943 and 1944 became the institutional baseline for maintaining every subsequent class of American surface combatant through the Cold War. And this channel intends to follow that story. Now, back to the yard. The 47,596 workers at peak were not 47,000 versions of the same job. They were organized by trade in one of the most rigidly specialized industrial workforces on the eastern seaboard. The riggers handled the crane work and the heavy lifting, anything that required moving large components between the ship and the shop floor. Moving a destroyer's main reduction gear, which weighed tens of thousands of pounds, required a rigging gang that understood the weight distribution of the component, the capacity of the available cranes, and the sequence of moves required to lower it safely onto a cradle truck without damaging the precision-machined gear faces. A mistake in rigging was not a quality problem. It was a crane accident. The Boilermakers did not simply fix boilers, and they worked the pressure boundaries of the entire steam system. The boilers, the pressure vessels, the steam drum internals, the header connections, the superheater elements. They tested hydrostatic, meaning they pressurized the system with water and watched for leaks at every fitting and weld. A hairline crack in a superheater header, invisible to the eye and undetected in a pressure test, could cause a catastrophic failure at sea when the system was under operating load. The pipe fitters traced miles of system pipe through the enclosed engineering spaces of a warship. A Fletcher-class destroyer had more than a mile of pipe in her machinery spaces alone. Installing or replacing that pipe required knowing not just where each run went, but why. What it served, what would happen if the wrong valve was installed in the wrong orientation, what the consequences of an air pocket in a fuel line would be at 30 knots in a beam sea. The electricians on combat system work were dealing with equipment that had not existed 15 years before the ships they were maintaining were designed. Radar, fire control computers, sonar, all of it required specialists who understood both electrical engineering and the operational demands of naval combat systems. And then there were the ship fitters, the welders, the painters, the insulators, the machinists. Every trade interlocked with every other. A ship that left the yard with a fitting installed wrong in a space where another trade had already completed their work required a decision about who would cut back their work to correct the problem, and who would have to do theirs again. The yard managed this through a work package system. Every ship entering the yard for overhaul was assigned a package of work orders, each one specifying the task, the trade required, the materials, and the sequence. The package was the contract. What was in it would be done. What was not in it required a separate authorization. The engineering plant of a World War II-era warship was not simple to overhaul. It was the most technically demanding work the Philadelphia Naval Shipyard performed, and the most consequential for what happened after the ship left. A cruiser, or destroyer of the period, was driven by a steam turbine propulsion system. Oil-fired boilers produced superheated steam at pressures between 400 and 600 pounds per square inch, depending on the class of vessel. That steam drove sets of high-pressure and low-pressure turbines connected through a main reduction gear to the propeller shafts. The reduction gear, a precision-machined set of bronze and steel gears running in an enclosed oil bath, stepped the turbine's operating speed of several thousand revolutions per minute down to the propeller shaft speed of under 200 revolutions per minute. While the tolerances on those gear faces were measured in thousandths of an inch. A gear that had been running under abnormal load, or that had been contaminated by water in the lube oil system, or that had simply accumulated enough operating hours to require inspection, came out of the ship and into the machine shop. Getting it out required the riggers and their cranes. Getting it into tolerance required the machinists and their precision measuring tools. Getting it back in required alignment work on the shafting system, a process of checking the concentricity of the propeller shaft from the stern tube bearing forward through multiple shaft segments to the reduction gear output coupling. A shaft that was out of alignment by even a fraction of a millimeter would vibrate at speed, damaging the bearings, the seal arrangements, and ultimately the gear itself. The propeller shafts themselves were removed through the stern of the ship, while in dry dock, examined for surface condition and internal integrity, measured for wear at the bearing journals, and either returned to service or replaced. A typical propeller shaft on a heavy cruiser was more than 18 inches in diameter and weighed several tons per section. The bronze propellers, removed by hydraulic press, went to the foundry propeller shop for inspection of pitch geometry, blade surface condition, and balance. This work did not happen one ship at a time. Multiple vessels were in multiple stages of the same overhaul process simultaneously. Each one in a different part of the yard, each one with its machinery staged across different shops on the island. But the yard was moving propulsion systems the way a railroad classification yard moved cars. The critical measurement was throughput. The 5 graving dry docks at League Island were not interchangeable. Each had been built to accommodate a specific size class of warship. And the escalating scale of American naval construction from the 1890s through the Second World War was written in concrete and stone at the bottom of each dock. Dry Dock Number 1, built in 1891, was the yard's original basin, designed for the steel cruisers of the new Navy that the nation began assembling in the 1880s. The Spanish-American War demonstrated that the existing capacity was insufficient, and a second dock was commissioned, completing in 1907, sized for the pre-dreadnought battleships of the period. The First World War and its immediate aftermath brought a third dock and the new construction infrastructure that accompanied it. But the decisive expansion came with the next war. In June 1940, as the Navy began planning for the construction of the Iowa-class battleships, ships that would displace approximately 45,000 tons at standard load and stretch 887 feet from stem to stern. The yard began work on Dry Dock Number 4. That dock, when it opened, was 1,092 feet long. Nothing in the American naval yard system was larger. A graving dry dock is, at its core, a concrete box with a watertight gate. When a ship arrives, the dock is flooded to the waterline. The gate is opened. The ship is warped in by tugs and mooring lines. The gate is closed behind her, and the dock is pumped down. The process takes hours. The ship settles onto a precisely positioned array of keel blocks, concrete blocks of calculated height arranged to support the hull at its structural strong points. So when the dock is dry, the keel blocks carry the weight of the ship, and the dock floor and walls are accessible for inspection and work. The pump-out rate at League Island's dry docks was substantial. A dock that size holds millions of gallons of Delaware River water, and reducing it to a workable level while maintaining control of the ship's buoyancy transition required continuous pump operation and careful monitoring of the keel block loads. A ship that entered Dry Dock Number 4 carrying battle damage, propulsion casualties, or accumulated wear had typically traveled thousands of miles to get there. The question the dock master asked when the water cleared was the same one the planners in Washington were asking. How long to return her to full operational capacity? And what was the next ship in the queue? The year 1944 was the year the Philadelphia Naval Shipyard ran at a pace the facility had never been designed to sustain, and held it anyway. Over the course of 1941, the workforce had risen from 24,000 to 33,000 workers. By 1944, it had reached 47,596 full-time civilian employees. And when summer students and military personnel were added, the island housed more than 60,000 people on a single working day. The yard operated on 3 shifts. There was no rest cycle for the facility itself. A dry dock that finished pumping down one ship began flooding for the next before the first ship had cleared the pier. The production figures from the war years are not simply impressive. They describe a different kind of industrial reality. In the period 1941 through 1945, the yard built 48 new warships and converted 41 more. It repaired and overhauled 574 vessels, completed and dry docked 650, and outfitted 600 more. The Naval Aircraft Factory on the eastern end of the island built 500 aircraft. The receiving station processed 70,000 Navy recruits. And in a wooden building on the island, unknown to nearly everyone working in the yard around it, Philip Abelson was developing the liquid thermal diffusion technique for uranium-235 separation that would contribute to the Manhattan Project. What the 30-shift production cycle meant in physical terms was that the yard's infrastructure was absorbing continuous use, without the maintenance intervals that peacetime operations would have allowed. Cranes ran, dry dock pumps ran, shop machinery ran. The electrical load across the island, sufficient to supply a mid-sized American city, was essentially constant. The workers who kept that load supplied were themselves running the same cycle. A boilermaker who finished a 12-hour shift on a destroyer in Dock 2 came back the next morning to find a different destroyer in the same dock. The sequence was the same. The ship was different. The standard did not change. The war ended in August 1945. By the end of 1946, the workforce at League Island had dropped to 7,500 workers. The production pace that had sustained 60,000 people on a single working day collapsed in under a year. What remained was the mission that would define the yard for the next 4 decades: repair and overhaul. The Navy's decision to stop building new ships at Philadelphia, a process that accelerated through the 1960s at the direction of Secretary of Defense McNamara, who moved construction contracts to private yards, transformed League Island from a balanced construction and repair facility into a specialized overhaul complex. By the time the Blue Ridge, a command ship, was completed in 1970 as the last vessel built at the yard, the decision had been institutionalized. Philadelphia would maintain the fleet. It would not add to it. The Cold War overhaul mission suited the trades workforce that remained: the machine shops, the boiler division, the electrical shop, the dry docks. The entire physical plant had been built to handle the most technically complex warships the Navy could produce, and it retained that capability. As the fleet's warships became more complex, guided missile systems replacing gun mounts, nuclear-powered propulsion plants in submarines, advanced electronics requiring clean room maintenance environments. The yard specialists adapted slowly by trade apprenticeship and accumulated knowledge. By the 1980s, Philadelphia was the Navy's designated overhaul facility for fossil-fueled surface combatants with high-pressure steam propulsion systems, advanced electronics, and sophisticated combat system installations. The ships that came to League Island were the ones that required the most skilled workforce and the most capable dry docks. When the Forrestal-class aircraft carriers required their service life extension work, they came to Philadelphia. The yard's final assignment a 2-year complex overhaul of the aircraft carrier USS John F. Kennedy, completed in September 1995, was completed 1 year before the yard closed. The Base Realignment and Closure Commission recommended the Philadelphia Naval Shipyard's closure in 1991. A legal challenge, filed by Pennsylvania's congressional delegation and supported by union leadership, delayed the shutdown for several years. The USS John F. Kennedy overhaul, completed September 13, 1995, was the final assignment. The last station log at the Philadelphia Naval Shipyard was entered on September 27, 1996. By that date, the yard had been operating on League Island for more than 120 years. Over that span, its total production encompassed not just the ships it built, the battleships New Jersey and Wisconsin, the carrier Antietam, the command ship Blue Ridge, and 70 others. But the far larger number it returned to service. 1,218 warships repaired, converted, or overhauled during the Second World War alone. Ships that had been torpedoed, bombed, and burned. Ships that had crossed thousands of miles of combat-contested ocean to reach the Delaware. Ships that, after months on League Island, crossed those same miles again in the other direction. What the Philadelphia Naval Shipyard represented was the maintenance spine of the American Naval War. A fleet that cannot repair its warships is a fleet in permanent decline. A fleet that can repair them faster than the enemy can damage them wins. The yard's physical legacy is visible at League Island today. The dry docks are still there. The hammerhead crane is still there. The brick industrial buildings that house the machine shops and pipe shops and boiler divisions are still there, occupied now by pharmaceutical companies and university programs and a commercial shipyard. The dry docks that held Iowa-class battleships now hold product tankers and government contract vessels. The institutional legacy is not visible. It is in the knowledge that does not transfer when a yard closes. The accumulated trade wisdom of machinists who knew which reduction gear designs failed at which components first. Of boilermakers who could read a hydrostatic pressure chart and locate a leak without pulling the fitting. Of riggers who had moved the same class of propulsion machinery so many times they had added their own refinements to the Navy's published procedure. If this story gave you a clearer picture of what held these systems together and what it took when they came under pressure, subscribe to the channel. And there are more yards, more ports, more operations, and more decisions still to document. Every naval battle the United States won in the Pacific depended on ships that had been repaired and returned to sea by workers on League Island. And that documentation is nearly gone now. The high-pressure steam turbine overhaul methods Philadelphia developed for Iowa-class battleships in 1943 and 1944 became the institutional baseline for maintaining every subsequent class of American surface combatant through the Cold War. And this channel intends to follow that story. And if you have a connection to this kind of work, a relative who spent decades in a roundhouse, a parent who worked a waterfront or a switching yard, someone who was there when a system like this was tested, tell us in the comments. Did someone in your family work at the Philadelphia Naval Shipyard? What shop were they in? And what class of vessel were they on when the war ended? The most complete record of how these systems were built and run isn't in any report. It's in the people who were actually there.